And then this is something else. Where does this come from? This comes from quantum mechanics. Okay. This comes from quantum mechanics. Given any simple harmonic oscillators, it has to have a ground state. This is the 0-point energy of a quantum harmonic oscillator. But if you let H bar go to 0, the above will become KBT. Okay. The above will just become KBT. So if H bar goes to 0, there will be no quantum mechanics in this wall. And we hope that has been the case. I just wonder what it would be if this wall has no quantum mechanics. Okay, then you get back the traditional Boltzmann's law, equal partition theorem according to Boltzmann's law. So if you add in this thing, you can come up with a new function which is very much like the density operator let me call this function theta. Theta of H bar omega naught. Okay? And I can call this E, because that is the E of each photon, and this is the E that we use in this thing. Anyway. So if you do that, then this can be written as this. This gives you the probability distribution of the energy that each state should have. And so depending on where you are, you will have this distribution. And this is very much like what they call the density operator. In quantum mechanics. So you can think of this as like the density operators for photons that are in thermal equilibrium. And this is a probability. Think of this as a probability. So this is like what we call a mixed state. The density matrix for a mixed state where all the states are not coherent with respect to each other. And you only keep the diagonal elements of the state. Okay. So if we put in this picture, we can have this density operator. And then you can actually get the photon density by integrating this thing. If you take the trace of this, you get the local density operator. If you multiply this by theta and integrate, you will get, I might be missing a delta function here somewhere. Maybe there should be a delta function here, I'm not sure. Okay. But finally you get this energy integral multiplying by this Planck distribution, multiplying by this and this might be something like going from all the energy levels that you have to E naught. This gives you all these photons that you can find in the system from this density of states thing. I might have some normalization factors out of place because I didn't see this being derived anywhere for photons. It has been derived for electrons. Okay, so this actually is the same statement as the fluctuation dissipation theorem. Okay, so this is what is called the fluctuation dissipation theorem, saying that if you know the local density of states, if you know the Planck distribution, you can find the photon density by using this formula. And this formula is only valid if your system is in thermal equilibrium with its environment. Because it's in thermal equilibrium with its environment, you can define a spectral Green function. That spectral Green function A corresponds to a lossless system, and everything there is in time harmonic oscillation. Okay. Because everything in there is in time harmonic oscillation, you can quantize and relate that to the quantum harmonic oscillator. In this kind of manner, I use this Planck distribution or generalized Planck distribution to write down the photon densities that you have in the system. Are there any questions so far? Well, we actually did this for infinite homogeneous medium. Then we asked ourselves, what change would there be if I were to repeat this derivation for a periodic structure? Say, instead of inhomogeneous, that if I have a structure where I put PEC objects in there, and then make them periodic, what would be the difference? The difference would be here that the difference would be here. That for a periodic structure, the vector wave functions will have new eigenvalues. For the homogeneous medium, the vector wave functions was very simple. We can still define vector wave functions that are of this nature, but the eigenvalues that this vector wave function have will not be the same as k. For the homogeneous medium case, we show easily that kappa n squared is just k squared for homogeneous medium, but this is not necessarily true for the periodic structure problem. Okay? Is this acceptable? Before that, we had three kinds of modes, N, N, and L. These three modes will all become different modes. There will be no decomposition into TE and TM, or vertical and horizontal. The vertical and horizontal polarized modes will be coupled to each other. The longitudinal modes will still be there. Okay, they can be decoupled from the transverse modes. Okay, so we still have a null space of this thing. We still have transverse modes. And we have to solve for this problem numerically. We have to find them numerically. So to propose a solution, you can propose that this eigenmode can be found with the Bloch-Locate theorem. Can be found with the Bloch-Locate theorem. And hence, this eigenmode will have something of this nature. G is my reciprocal lattice vector. I have to propose this kind of solution for that periodic structure problem. And then these are my unit vectors. Okay, EG1, EG2, and EG3 form a kind of if K plus G points in this direction, then EG3 points in that direction. EG1 and EG2 are any two vectors that are orthogonal. They could be horizontal and vertical. So these three can be orthogonal to each other. But EG1 and EG2 will not be decoupled from each other in this geometry. They will be coupled together due to the asymmetry that this system introduces. EG3 can still be decoupled, the longitudinal modes can still be decoupled from the transverse modes. And you have to find these modes numerically. And you will have to find these modes with the boundary condition that n cross f of n is equal to 0 on these surfaces. Okay. So you solve this as a boundary value problem. You find all these eigenvalues numerically. And this eigenvalues, case of n, of kappa n squared will be a function of k. That is, you can put in a block locate mode. This is just a block locate mode with a k vector. It will be a wave propagating through the system. Okay? And then your eigenvalues of this system will very much depending on which block locate mode you're finding.
What is kappa?
Kappa is just the new eigenvalues of the system. That need not be k squared. Before that, in the homogeneous mediums case, kappa n squared is k squared. But this is not necessarily true anymore. Okay, did you get that? Can you get that? Can you see that? No? Can you see that these eigenvalues would have to be different?
Yeah.
I call them kappa squared. Before that, there were three sets of them. One of them was 0, which is the L modes. The other one was the M and the N modes. But M and N modes are not necessarily decoupled from each other anymore. Okay, I call them kappa N. So you can think of it as this in a simple 1D case. Kappa. Before that, the 1D case, this is homogeneous medium. Okay, and then there will be n is equal to 1, n is equal to 2 modes. The M and the N modes are having the phi there. And then I will have a third mode, n is equal to 3 modes. It is down here. Always give me 0 eigenvalues. Those were the thing that was in the homogeneous medium. But in the inhomogeneous medium, the n is equal to 1 mode and n is equal to 2 mode need not be degenerate anymore. Just think of you introducing these scatterers in a very weak sense, make them small, and then make them bigger and bigger. Then those modes will start to split. Okay, the first thing is that they will start to split. Because they are not degenerate anymore. Maybe they will split like that. The n is equal to 1. I'm just hypothesizing that they split in this manner. The first thing that happens is that they split. The second thing that happens is that because you introduce periodic structures, there will be Brillouin zones introduced. The n is equal to 3 modes is still down there, doing nothing. So they will split, n is equal to 1, n is equal to 2, and then there will be Brillouin zones coming back like that, wrapping around. This is like aliasing, right? So if you're in one Brillouin zone, like 0, 2 pi over a or something in 1D, you'll see this kind of thing. So in this zone, you see the n is equal to 3 mode, n is equal to 1 mode, n is equal to 2 mode, and then you can see higher order modes wrapping back into your Brillouin zone. So n here can mean anything. It can mean the splitting of the previous modes you had in the homogeneous medium, plus the modes that wraps back into the Brillouin zone from the higher frequency mode from the other zone. This wrapping back is very much like aliasing in signal processing. Okay, once you put anything in a periodic structure, they start to alias back. So this kind of eigenvalue. So given any k values, you put in any k values in this system, you find this original mode that you have. You might even find this is kappa. Kappa n. This n is equal to 0, no, n is equal to 3, n is equal to 1, 2, and then the other ones. So this is your solution. And then in the place where they actually start to couple to each other, you find this very interesting thing that happens. From couple mode theory, you can show that this kind of thing should happen. When two modes are close to each other in wave number, and if they start to couple energy from one mode to another due to the fact that there will be scattering of one mode from another to another, you can write down the couple mode equations and show that they will split, something like that. And if the coupling is very strong, this diagram becomes very, very complicated. But you can still solve for this numerically, given any k value, find how many solutions there are. You can just mark your k value. The k value is determined by this block width k that you need in here. And then after you plug it in k value, you solve for your kappa n. And these are your kappa n. So this has to be a numerical procedure. It cannot be analytic. And after you've done this numerically, then the rest of the work is very similar to what we have done before. Okay, very similar to what we have done for the homogeneous medium case. You can also show that as a local density of states, there's also a spectral Green's function. Okay, and then the medium can be lossy, and then you can put in loss and then define this retarded Green's function together with this original Green's function. You can have a system that is always in time harmonic oscillation, and then you can relate this to the quantum state. Okay. And then you can do the rest. Are there any questions before we stop?
Is there a relation between the splitting and like how, how they come together when they couple?
The splitting assumes that they couple to each other and they transfer energy from one mode to another mode. It also can happen that the two modes don't interact, which happens in some cases. You might have some orthogonality principles that they cannot transfer energy from one mode to another. So if you look at very complicated waveguides, that does happen in some modes. It's impossible for this mode to transfer energy to that mode. In that case, it just cross each other. It just cross each other, and they just go like that.
Okay, but let's say they do couple, and does this slope have any effect on anything? Does the slope between them?
What happens is that you know that when things couple, okay, the group velocity has to be 0. Because the energy is kind of bounce back and forth between the two modes. So you always get 0 group velocity is one thing I know. Okay, and that's why you have this 0 slope thing. And then you can have slow wave and fast wave structures. But whether it does matter or not, I don't know how that helps with the coupling. But when this kind of thing happens, people call this a direct cone. Direct cone because it's somewhat related to a massless particle. Because if you have something with no mass, you always have a cone with it. This is a photon. Photon is 0 rest mass. So if you have particles with 0 rest mass, then you get the kind of cone. And this is of interest to people who study metal materials. And they try to construct periodic structures that have direct cones, and then they do fancy things with direct cones. Because the velocity of light is infinite, the mass of the particle is 0, at least the rest mass of the particle is 0, and it can do fancy things. So there are a lot of things to study in this field if you're interested. People did very fancy studies. Okay, any other questions? So maybe this is a good question for Tom for the take-home exam. I'm still thinking about what to give you for take-home. So if you want it easy, you can suggest me some questions. If not, keep thinking about some good.